Hello class, welcome to Stat 1200. I am your instructor William Buellman, and today we are covering section 7.1, confidence intervals for a population mean sigma known. Our objectives for today are to construct and interpret confidence intervals for a population mean when the population standard deviation is known, find critical values for confidence intervals, describe the relationship between the confidence interval and the margin of error, to find the sample size necessary to obtain confidence intervals of a given width, and to distinguish between confidence and probability. A simple random sample of 100 fourth graders is selected to take part in a new experimental approach to teach reading. At the end of the program, the students are given a standardized reading test. On the basis of past results, it is known that scores on this test have a population standard deviation sigma that is equal to 15. The sample mean score for the 100 students was X bar, which is 67.30. The administrators want to estimate what the mean score would be if the entire population of fourth graders in the district had enrolled in the program. The best estimate for the population mean is the sample mean, X bar. The sample mean is a point estimate because it is a single number. It is very unlikely that the sample mean, 67.3, is exactly equal to the population mean mu of all the fourth graders. Therefore, in order for the estimate to be useful, we must describe how close it is likely to be. For example, if we think that it could be off by just 10 points, we would write mu with the interval plus or minus that 10 points. So on the low end, we get 57.3 is less than mu, which is less than 77.3 on the high end, which could be written as 67.3 plus or minus 10, as I said earlier. The plus or minus number is called the margin of error. Suppose we want to be 95% confident in our interval that we create. We need to determine how large to make the margin of error so that the interval is likely to contain the population mean. To do this, we use the sampling distribution of X bar. Because the sample size is large and is greater than 30, the central limit theorem tells us that the sampling distribution of the sample mean is approximately normal with a mean mu and standard error of sigma over the square root of n. So here would be a sample of the sampling distribution. For the teaching example from earlier, the standard error, which is sigma over the square root of n, would be 15 over the square root of 100, which is equal to 1.5. We now construct a 95% confidence interval for the population mean mu. Begin with a normal curve and find the z-scores that bound the middle 95% of the area. So remember, this is the middle 95 under the curve. The z-scores are negative 1.96 and positive 1.96. The value of 1.96 is called the critical value. To obtain the margin of error, multiply the critical value by the standard error. So the margin of error in this case is the critical value times the standard error, which is 1.96 times 1.5, which gives us 2.94. So to create a 95% confidence interval for mu, then we have, remember, it was X bar plus or minus the margin of error. So that's going to be 67.3 plus or minus 2.94, which is equal to 64.36 is less than mu, which is less than 70.24. So what we can now say is that we are 95% confident for that example that the population mean is between 64.36 and 70.24. 4. Based on the sample of the 100 fourth graders using a new approach to teach reading, a 95% confidence interval for the mean score was constructed. 95% is the confidence level. For the confidence interval. The confidence level measures the success rate of the method used to construct the confidence interval. If we were to draw many samples and use each one to construct a confidence interval, then over the long run, the percentage of the confidence intervals that cover the true value mu would be equal to the confidence level. So what this is showing in this graph right here is if we took multiple samples, so each one of those blue lines is a sample, you will see there's a few of them, like one right here, another one right here, another one right here. But for the most part, most of them do capture the true mean of the sample. So here, what this is showing is that occasionally we will get one that doesn't calculate the true mean. That's why we're saying we're 95% confident, because there might be a chance that we didn't capture the true mean. A point estimate is a single number that is used to estimate the value of an unknown parameter. A confidence interval is an interval that is used to estimate the value of a parameter. The confidence level is a percentage between 0 and 100% that measures the success rate of the method used to construct the confidence interval. The margin of error is computed by multiplying the critical value by the standard error. Although 95% is the most commonly used confidence interval, sometimes we will want to construct a confidence interval with a different level. We can construct a confidence interval with any confidence level between 0 and 100 by finding the appropriate critical value for that level. The critical values for several common confidence levels are given in the bottom row of table A3. So if you look at the bottom of table A3, you'll see that with these z-scores is the confidence interval level. So if we want a 98% confidence, we would use 2.326 as our critical value, as we already saw with the 95% confidence interval, which was 1.960. So if I give you just, let's say, a 99% confidence interval, you would come to this table, look, and see, oh, that for 99% confidence, the critical value is 2.576. Example 1. A large sample has mean 7.1 and standard error of 2.3. Construct a 90% confidence interval for the population mean. Again, if we go to table A3 and we looked at the 90% confidence, we would see that a critical value there is 1.645. So our margin of error is our 1.645 times our standard error, which is 2.3, which gives us 3.8. A 90% confidence interval for mu would be, remember, it's x plus or minus our margin of error, which is in this case 7.1 plus or minus 3.8, which gives us 3.3 is less than mu, which is less than 10.9. So we are 90% confident that the population mean for this example is between 3.3 and 10.9. Sometimes we may need to find a critical value for a confidence level that's not listed in table A3. So if it's listed in table A3, you're done. This is for if you're not listed in table A3. To do this, it is useful to learn a notation for a z-score, which is the given area to its right. The notation z sub alpha refers to the z-score with an area of alpha to its right. So we'll see this in examples, don't worry. The notation of z alpha divided by 2 refers to the z-score with an area of alpha divided by 2 to its right. If 1 minus alpha is the confidence level, then the critical value is z alpha divided by 2 because the area under the standard normal curve between negative z alpha divided by 2 and positive z alpha divided by 2 is 1 minus alpha. So that may seem confusing, but remember, we want the middle 95% or whatever percentage for the confidence interval. So in this case, like I said, if I want 95%, that means I have my alpha is 5%. So I need 2.5% to the left and 2.5% to the right because I'm trying to get that middle 95%. And that's what this is showing. You have the shaded area, which is your middle part, and then you have half of the remaining area that you don't want on each side. You can use table A2 to find these z-scores. Example 2. Find the critical value z alpha divided by 2 for a 92% confidence interval. Again, the confidence interval is 92%. 1 minus alpha is equal to 0.92. It follows then that alpha must be 0.08, or alpha by 2 divided by 2 is 0.04. The critical value is z sub 0.04. The area to the right of z sub 0.04 is 0.04. The area to the left is 1 minus 0.04, which is equal to 0.96. So just here is a graph of that. Using table A2, we can find the critical value to be 1.75. So what we're trying to do, again, is since the left-hand area is 0.04, we have to add up the middle and the right, which gives us 0.96. That's what that says up top. So now we go to our table A2 and we're looking for the closest z value that is equal to 0.96. So if you look here, we found in the table 1.75 is equal to 0.9599. So that is the closest value to 0.96, so that is our z-score, or our critical value in this case. In order to do this, we're making some assumptions. The method described for confidence intervals requires us to assume that the population standard deviation, sigma, is known. In practice, sigma is not known. We will make this assumption because it allows us to use this familiar distribution. We will learn how to construct confidence intervals when sigma is unknown in the next section. Other assumptions for the methods described here for constructing confidence intervals are as follows. We need a simple random sample, and the sample size needs to be large, greater than 30, or the population needs to be approximately normal. Example 3. A machine that fills cereal boxes is supposed to put 20 ounces of cereal in each box. A simple random sample of 6 boxes is found to contain a sample mean of 20.25 ounces of cereal. It is known from past experience that the fill weights are normally distributed with a standard deviation of 0.2 ounces. Construct a 90% confidence interval for the fill weight. So first, we check our assumptions. Simple random sample. It said it was from a simple random sample. Check. So is it greater than 30, or is the population approximately normal? It said that the pop was approximately normal, so we're going to use that. So check. So our assumptions have been met, so now we may continue. Since the sample is from a simple random sample and the population is known to be normal, the assumptions are met as we just shown. The point estimate is the sample mean, which is 20.25. The desired confidence level is 90%, so we look at table A3, find this 90%, and we see that the critical value is going to be 1.645. The standard error, sigma divided by the square root of n, is 0.2 divided by the square root of 0.6, which gives us 0.08165. So the margin of error now is, remember that critical value times our standard error, so we have 1.645 times our standard error, which is 0.08165, which gives us 0.1343. So that is our margin of error. For the 90% confidence interval, remember it is x bar plus or minus the margin of error, which is 20.25, our sample mean, plus or minus 0.1343, our margin of error, which gives us 20.12 is less than mu, which is less than 20.38. So we can say now that we are 90% confident that the mean weight for these cereal boxes is between 20.12 and 20.38. If we want to be more confident that our interval contains the true value, we must increase the critical value, which increases the margin of error. There is a trade-off. We would rather have a higher level of confidence than a lower level, but we would also rather have a smaller margin of error than a larger one. So this is shown in the three graphs down here. If we're willing to take a 70% confidence level, we see that although the margin of error is smaller, it only covers the population mean 70% of the time. So often our sample may miss the true population mean. 95% confidence, this represents a good level of compromise between the reliability of the margin of error for many purposes. So here we cover most of the population mean with most of the samples, and it's not too big of a sample. If we go to 99.7 confidence level, they almost always succeed in covering the population mean, but the margin of error is also large. Look at how large the margin of error is. Yes, we almost always hit the population mean, but because of that, we have a very big spread. So we need to figure out that balance between how much spread do we want and how much accuracy do we want, and that's what this is saying. The diagram presents 100 different 95% confidence intervals. When we construct a confidence interval with level 95%, we are getting a look at one of those confidence intervals. We don't get to see any of the other confidence intervals, nor do we get to see the vertical line that indicates where the true value of mu is. We cannot be sure whether we got one of the confidence intervals that covers mu, or whether we were unlucky to get one of the ones that is unsuccessful. What we do know is that our confidence interval was constructed by a method that succeeds 95% of the time. The confidence level describes the success rate of the method used to construct a confidence interval, not the success of any particular interval. Here we go. This is just the diagram that I was talking about. We've seen them before. If we had 100 samples here, what this is saying, we expect 95 of them to cover the true population mean, and there will be 5 of them that do not cover the population mean. We can make the margin of error smaller if we are willing to reduce our level of confidence, but we can also reduce the margin of error by increasing the sample size. If we let m represent the margin of error, then m is equal to the critical value times the standard error, as we've seen. Using algebra, we can rewrite this formula to get that n is equal to that critical value times sigma, the population mean, divided by m, the margin of error, and all of that squared, which represents the minimum sample size that is needed to achieve the desired margin of error m. If the value of n given by the formula is not a whole number, round it up to the nearest whole number. Always round up for n in this case. By rounding up, we can make sure that the margin of error is no greater than the desired value of m. Example 4. Scientists want to estimate the mean weight of mice after they have been fed a special diet. From previous studies, it is known that the weight is normally distributed with a standard deviation of 3 grams. How many mice would need to be weighed so that a 95% confidence interval will have a margin of error of 0.5 grams? Since we want a 95% confidence interval, we use z alpha by 2 equaling 1.96. We also know that sigma is equal to 3 and that the margin of error is equal to 0.5. Therefore, we get that n is equal to that formula, which is 1.96 times 3 over 0.5 squared, which is equal to 138.30, which we're going to have to round up to 139. So we must weigh 139 mice in order to obtain a 95% confidence interval with a margin of error of 0.5 grams. Suppose that a 90% confidence interval for the mean weight of cereal boxes was computed to be 20.12 is less than mu, which is less than 20.38. It is tempting to say that the probability is 90% that mu is between 20.12 and 20.38. The term probability refers to random events which can come out differently when experiments are repeated. The numbers 20.12 and 20.38 are fixed, not random. The population mean is also fixed, even if we do not precisely know what that value is. The population mean weight is either between 20.12 and 20.38, or it isn't. Therefore, we say that we have 90% confidence that the population mean is in this interval. On the other hand, let's say that we are discussing a method used to construct a 90% confidence interval. The method will succeed in covering the population mean 90% of the time and fail the other 10% of the time. Therefore, it is correct to say that a method for constructing a 90% confidence interval has a probability (90% of covering the population mean. So the method has a 90% probability of getting the correct population mean.